So I think I've sent you an email, right, which would have a kind of checklist of revision topics on it. I mean, perhaps we'll look at this in a moment. So the idea of that particular checklist is it's just that. It's a list of bullet points. It's not a recipe for saying you have to learn exactly everything on this sheet and nothing else. It's saying that, it's supposed to be a guide, a sort of aide memoire for when you're doing your revision. So you can just go down the bullet points, as it were, and kind of check them off as you go through. So there are a list of things that I kind of pick out and just think of the salient points, all the important features of the course there. So that's just to sort of help you kind of fix your mind on what to do to go through. And for these revision sessions, so there are 6 of these, and we're going to have 2 of these in what were the lecture times in the previous weeks, so today and tomorrow. And then the third one is on Friday, in what was the problem session slot. So the idea is that these are all live online sessions, so you can ask questions in real time. If this is not enough time and people send me, oh, I want to see how to do exercise this, or I'd like to go through the proof of theorem so and so, then I can record an extra asynchronous slot and actually just kind of put it up there on YouTube and tell you about it. Right? But at the moment, there are going to be just these 3 revision sessions for this week, in week 11, and then the same again in week 12. So that's when you come back after the break. And previous years, what I've done is, I suppose, just taking questions from people. And if there aren't any questions, go through some of the text and perhaps do some relevant, or redo some relevant questions that were either in the exercises or on past exams. So coming to the exam, of course, now it's slightly different from previous years. You can find 3 years worth of old exam papers up there on Blackboard, one of which there are solutions for. So we don't put solutions up for all of the exams. I mean, it's thought pedagogically better to actually have people work through or try and go through those exam questions on their own. But there is one kind of model solution set up there to kind of show you how much perhaps you need to write, or to give you some idea of the sort of tenor of the answers that's there. So sometimes people ask for solutions for other years, but I shan't be giving those out. Right? It's just for the one that's there. And of course, the exam is slightly different in that now it's open book. So you will have your notes and access to the internet and anything else that you want. And so what will actually happen is that the questions will be actually not terribly different from the ones that are there on the open book exams. But what will happen, of course, is the ones that are, say, give the definition of this, give that proof. So they will be changed, right? Because of course, you can just write out what the definition is there in the notes, right? So there won't be questions that say, give a definition of what a transitive set is, right? What there will be is some question, there will be some variant on perhaps what a transitive set is and ask you to say something about it. So it wouldn't be immediately just the bald, write down this definition. Right? Still means you have to know the definition, but also because you have to understand the definition, right? So to be able to say a little something about it, right, there. So those, and of course, these were kind of traditionally perhaps in the earlier part of the questions. So those will have been tweaked. Right? Nevertheless, I think the past exam papers are a good guide for what's coming, and the best way to revise the exams, as I say, every time and for every course, is go through the exercise sheets, go through the old exam papers. So in a sense, that's what I'm doing, but I will perhaps preface I will preface that by going through some of the text, right? The important bits of the text. For the third year set theory course, this was somehow organized itself a bit more simply because there were 6 chapters and 6 revision sessions. So I concentrated on each revision section on 1 chapter. And I think today I will just concentrate on, well, the beginning part of the notes here. But that said, these sessions, these are all for you, right? So if you want something particularly different, just speak up. It doesn't matter to me what I do. You can ask for particular exercises, particular theorems to be gone through, and we can cater for that. If not immediately at the moment you send the question through on chat, then at some point. And of course, you can always email me, right, if you've got something that you want done, or if you've just simply got questions. So please just use the email there as well. What I've also done for this exam is I've set the last question, question 4. This will be an essay style question, right? So, I mean, this is also mindful of the fact that the people in the Logic and Philosophy of Maths MA, but it's an essay that will be something about the construction of L and talking about how L makes various mathematical statements, as it were, safe for mathematicians.
I wonder where that bit of my tooth went.
I'm sorry, was that a question or just an unmuted?
Oh, sorry. Yeah, no, I'm not muted.
Okay, that's all right. So of the 4 questions, one will be this just a one part, as it were. One whole question will be write an essay on this topic or on either of these 2 topics here. Right. So you might want to, I urge people to think about kind of broadly what we did with the constructible universe, what Gödel's theorems were about, proving the consistency of the axiom of choice or the continuum hypothesis. Right? And the phrase I used was making these statements, as it were, safe for mathematicians to add to their set theory. Right? So, such an essay it'll say some details there about what's expected, and this will say, that you're supposed to put down some details of the construction. Right? It won't just be a completely English word essay. So think in your minds, kind of summarize, right? In your minds, draw out on a piece of paper a list of, how we constructed L, how we used L as being absolute in its definition, that we showed that the axioms of ZF were true in L. And then we showed various statements like V equals L or AC or GCH were true in L. And then we showed that this meant that if the theory of ZF was consistent, so was the theory of ZF plus AC. Right? What were the steps there in that reasoning? So this is something you can, of course, well work out in advance, right? What kind of thing you might want to say in these circumstances. Right, so that's a kind of heavy hint, I suppose, telling you what's going to be there in that question 4. And any questions at this point? Okay. Does this sound like a reasonable plan for these revision sessions? Does anybody has got any particular requests for this? If so, do send them through. Or unmute. There's not many of us here, so we can always talk. Okay, then. Let me share the screen then for a moment. Except I can't find what. Sorry, it seems to be taking a minute or two. You're gonna have to try it again. It's saying screen sharing is failing to start. Okay. Okay, so this is the revision topics checklist here. So I mean, basically, I can go through these. I mean, roughly what I'm going to be doing, I suppose, is going through the things on this list. I mean, I've claimed that the list contains the important items, so that's kind of what I'm going to go through. 2 to 5, I've mentioned here. These are things from the third year set theory course. So unless you ask me, I won't be saying very much about these things. But of course, you can ask me about anything. So what we have is things grouped. Up at the top here, we've got basically the ZFC axioms in a form given using terms. So again, I'll remind us about what those terms are and those axioms first. Right? I might mention, our definition of transitive closure, and then I'll talk about relativizations. Okay, here. I'd like to point out one thing. Sorry, this is an aside. So Omari pointed out to me that the general exercise solutions, I've got, as opposed to the course notes, I've got 1 and 2 interchanged. So actually in the course notes, this is number 2, and this one down here is number 1. So it's a bit confusing because they're numbered incorrectly. So next year I'll be changing around this 1 and 2 here. Okay. So terms, then what were terms? So they may seem slightly mysterious at the beginning, right? But it's a way of enhancing our language without enhancing our language. Right? Well, so our official language, script L, where we discuss sets, just has equals sign in it and a membership symbol. And to the left of the membership symbol goes a set, and to the right of the membership symbol goes either another set or a class. Right? So it could be that there are things that we want to talk about which are kind of too large to be sets, right? And we think of these as proper classes, right? I mean, if you look in some textbooks, they call everything classes, and then they divide those into two kinds. Those classes that are sets and those classes that are proper classes. And I tend to kind of keep the terminology apart, right? But it's quite common. You define something and you say, okay, it's a class, and then you determine whether it's actually a set or a proper class. So terms are a kind of syntactic device as a way of defining classes. So the term may end up being a set, or it may end up being a proper class. And typically, here you can see here under R in the middle, top of the middle of the page here, R, the Russell class, right? This is this so-called paradoxical class. It's a collection of all sets X which are not members of themselves. So a term typically then is something like this. You know, there's some curly brackets. It's saying the collection of things X or Z, and then there's some expression. Some expression which involves, I mean, should involve the X if it's going to be meaningful here in this case. So likewise, has something happened to the sharing? I'm getting a little sign saying sharing has been paused. Now I'm wondering whether the whole meeting has stopped. Okay, yeah, sharing got paused for some strange reason. Okay, I'm going to start it again and see what happens. Okay, hopefully it starts again. Just a moment, I'm going to stop it again. I want to see if I can kind of get the chat independently of the. Okay. Right. Okay. So not quite sure when the freezing started. I was talking about terms, and here is a typical term. You know, it's something in parentheses like this, consists of an X, and then there's a specification. And this is, you know, simple specification. X is not a member of X. So this is something in our official language. So we're going to add things like this express syntactic string to our official language. And here's another one. V is the term of all sets X such that X equals X, right? Well, that's everything. So that's going to, V will be all sets in that case. And we can stack these things up. We can have, although we add this syntactic string to our language, sort of expand the language a bit, we can allow formulae with terms in to appear in these specifications, right? As long as we're careful, we just build these things up inductively. So here's the official definition of terms, and it's clean or neat to actually classify just variables, v0, v1, v2. We call those terms. And although I often slip, a term t can be either a variable or one of these class terms. Right? And we say here is a class term is a symbol string like this. And x is sort of like a meta variable. It stands in for one of the variables, vk, and phi is a formula. So the term is about the collection of x's such that phi of x. So x is now involved in this term. So it's not really a free variable floating around, right? Because now x has become connected with the formula that's talking about it inside the term. So x is not a free variable of this expression. So that's what's being said here. The free variables of a term are, those are the formula, which is doing the specification, minus the thing that's being specified about here. And to keep the definition clean, if x itself just is a variable, this very simple term, then it's just its own free variable. Okay. And we're allowed to substitute terms in for variables. There's some usual kind of restrictions on this. I mean, which I haven't specified, right? Which is something that people, worry about in logic courses. A variable of the term in the specification of this term itself, the t, it's specified by some formula of psi, and it may use variables which clash with the variables in the quantifiers of phi. Well, we just pretend this doesn't happen. We just change the variables in t to something else. So we can substitute a term for a variable. Right? So then one has to ask, well, what does it mean to say that y is a member of this term, or two terms are equal? Right? Or the set equals this term. Well, this term is a member of that term. And that's what this recursive or inductive definition does here, right? It takes the thing on the left and says, this is an abbreviation for the thing on the right. So very simply, to say that y is one of the x's specified by phi is just to say, well, phi of y holds. And this is y being substituted for x. And to say these two terms are equal is to say, well, anything that satisfies this specification satisfies that specification. And that's all this says here. And so on. Right? So although we're talking about, saying what this term being a member of this term is, right? It is actually a proper inductive definition. Notice that this says here, this is a member of that. Well, this is only going to work if the thing to the left of the epsilon is a set. And that's what the right-hand side says. It's a no-no to start talking about proper classes being members of things. Proper classes aren't members of anything at all. So it says there is a set y, using lowercase here for these set variables. There's a lowercase y, which is this term, and psi holds of that y. Okay, so this expands our language. If there are any queries here. So here are some terms. Right? Here's the empty set. Right? Here's V again. And here's a bunch of ordinary set theoretic definitions down here. Right? Here's an unordered n-tuple of things, right? Saying that X is this one or that one or that one or that one. Right? So included in this is that these TIs better be sets because they're members of something else. Right? Ordered pairs, Cartesian product, power class, so on. Okay, we won't go through them too closely. So now we list our axioms. So this says something about these two terms. It says that this one is a member of that one. So actually, this is a set existence assertion. Remember that to say that some term is a member of another term is to say the thing on the left is a set. That's the first thing it's saying. Then the second thing is it's saying the set on the left satisfies the right-hand specification. So to say that the empty set is a member of V, right, is to say this is a set and it equals itself. Okay, and that is true. So we take that as a true axiom. Pairing says, okay, I've got for any two sets X and Y, this set here, this thing, right, this expression gives me a set in V. So I can interpret this as saying, for any X and Y, this class consisting of either X or Y, this is a set. So these are actually set assertions, right? These first three axioms. There's kind of an implicit kind of universal quantifier here. I mean, it doesn't say for all X, for all Y. This thing here is in V, right? I mean, actually, if one thinks about it a bit more, what it's saying is that this term here is in V. Right? And I said before, X and Y stand in for any variables. Right? So it's kind of traditional not to write for all X here, or in number 3, for all X, big union of X is in V. But it's kind of implicit here that this is talking about all X's and all XY's. Okay, so some more definitions, what something it is to be a relation, right? The domain of a relation are the things in the first coordinate, the range of the relation things that appear in as a second coordinate over here. And here there's some elementary definitions about what functions are. Right? Okay, so I won't do everything again. Here's a list of our axioms, if you need to find them. Extensionality, again, which is important, of course, although very simple. Right? It's criteria for when two sets are equal. They have the same members, and that's all we care about. And slightly more sophisticated axioms here. Right? So basically, again, it's saying something is in V. So it's saying that the thing on the left is a set. So the members of X that satisfy the specification which defines the term A. So we separate out from X those elements which satisfy the specification for A. And that's true for any term A, right, here. So we take that as an axiom. Right? And the power class, again, of X, this is an axiom that says that it's a set. Right? Okay. So let me, let's see how the time is going. Let me talk about relativizations. Right, so this is a feature that occurred a lot. We defined simple formulas. These are the bounded ones here, right? And we called these the delta zero formulae. So atomics, these are literally just what's equal to what, what's a member of what. These are delta zero. So basically a delta zero formula is one which you can kind of verify by just looking at a set and looking inside it and seeing whether the formula is true. It doesn't refer to things in the rest of the universe because any quantifier that it has just says there's something inside one of these, or for everything in here, something holds. Right? So there is no unbounded search, if you like, through the universe to see whether there exists an X that's something or other. So these delta zero formulae are things that we call absolute, and they're the kind of specify the simplest concepts. And something is a sigma one formula, right? If it's a delta zero with an existential quantifier in front. And it's a pi one formula if it's a negation of a sigma. That is, it's a formula with a delta zero formula with a universal quantifier in the front. Relativizations then. So the spirit of relativizations, I mean, you can simply say what a relativized formula is. The formula we're going to relativize to the term. As we write it down, as you can see, it's a formula with this superscript and this term. So again, W, the term here, this is one of these syntactic strings inside curly parentheses. But we're thinking that this term is a collection of sets, well, as it is, right? So I can relativize any formula to a term by just basically, the last clause is what's important. I take the quantifiers in the formula and I just restrict them to the term. Right? So there exists X in W. Right? So now I bound the quantifier by the term. So it's saying whatever this expression concept expressed before, now it's only talking about the things in W. So to check, again, whether this formula comes out true in W, you just have to look inside W. It's not about anything outside W anymore. So we can relativize our concepts to terms. And later we'll think of these terms as being like transitive ZF minus models. So they're like mini universes. They're like collections of sets which satisfy a lot of our axioms. And so they're worth thinking about. And there are quite a few lemmas about relativizations here. I mean, not all, you don't want to, commit all of these to memory, but you should get the kind of ideas as to what they're about, right, here. An important feature of a term is if it's transitive, then the axiom of extensionality holds, relativized to W. And this is a formal proof of that, right? It takes the axiom of extensionality, it looks at what relativization means when it kind of unpicks what that axiom looks like in terms of quantifiers. And basically, if you look here, those unbounded quantifiers in the axiom, they've all become bounded quantifiers, bounded by the term W here. And the atomics relativize to themselves, and that operation of relativization commutes with the propositional connectives there. So this is a sort of safety lemma, if you like, right? It shows that our ideas work well. Right? If I've got a formula and I stick in some terms and I relativize it, I get the same thing as if I take the relativized formula and stick in the relativized terms. So again, we didn't prove that. And these lemmas here just say something like, if I've got a transitive term and I've got if any two objects in W, this pair set is in W, then if I were to actually look at the axiom of pairing and relativize it, I'd see that that was true in W. And it's kind of, you might be tempted to say, well, obviously, because you put into W in here any unordered pair. Indeed, that's true. So if W is closed under certain operations, then that axiom will be true in W. So if omega is in W, W will think the axiom of infinity is true. Kind of obvious, right? But one can give formal proofs of this just looking at how we syntactically relativize our axioms. But on the whole, I mean, these proofs are kind of, I mean, you probably remember I skipped them. I mean, they're somewhat uninteresting, right? Not very instructive. 127, again, it's in the same spirit. If I've got a transitive term, and if the power set of X is in W, then it thinks the axiom of power is true. Okay, so I'll pause for a moment. I was thinking I might mention something about absoluteness now. But if anybody wants to ask about what I've just zipped through there, then okay. Let's go to the so absoluteness. Okay, so this is an important property. Often we want some concept to have the same meaning about sets in some term W as it does about those sets in V. Often we specify that W is closed. Transitive, so it has no epsilon holes in it. So it's closed under not. So it has all the epsilon information about any of the sets, because any set is a subset. And we ask that it's a model of a lot of axioms, all the axioms except power set. So, and you'll have seen this diagram, and you may be fed up with this diagram by now 100 times. Here I've got a term W, or a picture of it, and somewhat without prejudice, I've drawn it rather as a set. It doesn't contain all the ordinals. It doesn't go up to the top of the universe. So probably this W is a set. And the idea is we may have some sets here, X and Y, and we may have some concept, right, X and Y, and it may be that phi holds of X and Y in V. But then the question arises, does this hold if I relativize these quantifiers to W? So if yes, we say it's downward absolute. And if no, well, then it's not. I won't write anything more about that. And you can ask the question the other way around. If W sees a certain property of X and Y, does it mean that it's true in V? So if you like, there's a kind of hidden V in here, right? But this kind of doesn't make sense, because to relativize a quantifier to V is not to relativize it at all, because the quantifier still ranges over all the sets. So we don't write this here. So the answer is yes, in this direction, it's going upwards absolute. So it's going from W up to V, right? And it's absolute if it goes in both directions, right? Now, if W is transitive, simple things are absolute. Right? Sorry, that says if W is transitive, then simple things are absolute. For example, X equals Y. If W thinks X equals Y, it really does equal, they really do equal each other, because X is a subset of W and Y is a subset of W, because we specified W transitive. So W knows all the epsilon information about these gadgets. So W can tell whether they are equal or not. So in fact, any delta naught expressible concept is absolute for transitive W. So in chapter 3, we saw quite a lot of delta zero expressible concepts here. Right? So it's not just equals, but all of the kind of things we were talking about here, U cross V, right? F is a function, right? F takes alpha into beta, right? Well, I've already started using ordinals. Alpha is an ordinal here. All of these can be written using delta zero formulae. So this means then, right, particularly if W is transitive here, I should say I'm a little bit, yeah, no, okay, that's right. I don't think I said anything wrong here. So if W is transitive and it's also a ZF minus model, then it can form things like pairs and unions and Cartesian products, because those axioms, anything that you can form in set theory without the power set operation, W will have something like that in there, if it's a model of ZF minus as well here. And we thought kind of, I mean, I hope it was sufficiently clear. Right? Start on another piece of paper. Whether something is a okay, here's my W and my V. I may have some X and some Y. And maybe in V there is a function from X onto Y. So this would imply, okay, the cardinality of Y is less than or equal to the cardinality of X. Because I've got an onto map from this onto this. So Y can't have a larger cardinality than X. But of course, this F could exist somewhere outside in V. F needn't be in W, even though X and Y are in W. Again, nothing to do whether W is a model of ZF minus or not. Right? It's just a question of what things there are inside W. So, so this relation here, right, is not downwards absolute. It might be true in V, the sum F, but not in W. And this here, this is a sigma 1 statement. It's saying there exists a function which does something. So we have an existential statement saying this function exists, and it's true in V, but not in W. So sigma 1 concepts are not downwards absolute. But a pi 1 concept that says something about for all Fs or Gs, that will be downwards, because if it's about for all, it's about all of those that are in W as well. So pi 1 is downward absolute. So an example here. Right, alpha is a cardinal. Right, this is pi 1. Because it says for all functions F, if the domain F is beta, which is less than alpha, and F goes from beta to alpha, then it's not onto. Right? Being a cardinal means you're bijective with something, being a cardinal, being not a cardinal means you're bijective with something smaller. Okay, so here we're going to say the opposite of that. For any function, right, if its domain is something smaller, this is not a bijection. So there's no map from alpha to something smaller, so it's a cardinal. But this is a pi 1 thing. It talks about all functions. So if this is true in V, it's about all possible functions there are between alpha and beta, between alpha and something smaller. But that includes the functions that are in W. So W must also think that alpha is a cardinal. Down here. But again, the converse doesn't happen. If something is pi 1, it's not upwards absolute. Which is kind of just by taking negations, right, really. So conversely, sigma 1 is upward absolute, and pi 1 is downward absolute. If alpha is a cardinal in W, This does not imply that alpha is a cardinal. Okay. Well, time is up there. I didn't answer any questions. I just seemed to go through this theory. I don't know whether that was the most useful use of time or not. But if there are particular questions relating to relativizations and this absoluteness, then either send them through by email to me or save them for the next session tomorrow.